Let's jump right into this explainer and unpack exactly how engineers take literally the most high-stakes, inherently dangerous systems on Earth and systematically make them safe. Whether we're talking about a sprawling rail network, a massive power grid, or some seriously complex industrial machinery, safety is never just a happy accident. It's meticulously engineered. So today, we're going to explore the precise, real-world frameworks used to mitigate risk and actually guarantee safety in these incredibly complex environments. Here's our quick roadmap for this explainer. We'll start with the reality of risk, move into the hierarchy of control, discuss the temptation of easy fixes, dive into proving safety with the safety case, and finish up with the final defense. Section 1, the reality of risk. This right here is the ultimate engineering question. How in the world do we reduce either the likelihood or the severity of harm? Well, to answer that, we really need to understand a core concept. Safety isn't just a single feature you can just bolt onto a machine at the last minute. It's what we call an emergent property of a well-integrated system. It's kind of like a giant puzzle. Safety only actually exists when every single piece, the hardware, the software, the human operators, and the physical environment itself are perfectly brought together and interacting smoothly. If even one piece fails, that whole emergent property of safety can just vanish. A railway level crossing is honestly the perfect running example for us today. Think about it for a second. This represents the continuous, everyday challenge of separating vulnerable people from massive, high-speed hazards. You've got pedestrians, distracted drivers, unpredictable weather, all directly intersecting with hundreds of tons of metal hurtling past at high speeds. How do engineers systematically guarantee that a disaster doesn't happen here every single day? Section 2. The hierarchy of control. Engineers systematically tackle these hazards using an inverted pyramid known as the hierarchy of control. It's basically a visual representation of how we absolutely should prioritize our risk reduction. You always start at the top, the widest and most effective part of the pyramid, and you only work your way down to the bottom, which represents the least effective, least sustainable methods. So the crucial takeaway here is that we must always strive to start at step 1, elimination, and only move down this list when the higher-level interventions are literally impossible to achieve. As we drop down from elimination to substitution to engineering controls, down to administrative controls, and finally personal protective equipment, we are drastically increasing our reliance on human participation. And honestly, as we're going to see, that's a pretty risky bet. Let's actually apply this entire framework directly to our level crossing example, step by step, to see how this builds our safety net. Starting at the very top, elimination. The absolute best thing we can do is just design the hazard out entirely. Just remove the road crossing so the train and cars literally never meet. Now, if we can't do that, we drop to substitution. We replace the hazard with something less dangerous, like building a bridge over the tracks. But notice, this isn't flawless. Bridges introduce brand new hazards, right? Like vehicles falling onto the tracks or tall trucks striking the bridge from below. If a bridge is totally impossible, we fall to engineering controls. These are technical measures that physically separate people from the hazard. Think automated barriers, warning lights, and interlocking systems that automatically stop the train if the barriers fail to lower. Below that, we're relying on administrative controls. This is rules and training, simply teaching drivers how to navigate the crossing. And at the very bottom, our absolute last resort is personal protective equipment, or PPE. For a road crossing, this obviously doesn't do much for a driver inside a car, but for trackside workers, it means wearing high-visibility clothing just so the train driver might spot them in time to sound the horn. Section 3. The temptation of easy fixes. Now, organizations are constantly tempted by those lower levels on the pyramid, administrative controls and PPE. Why? Because, frankly, they are vastly cheaper and faster to implement than, say, building a multi-million-dollar bridge or installing complex automated barrier systems. But here is the fatal flaw with that logic. Humans are unreliable. Under stressful conditions, people make mistakes, they totally forget their training, they ignore warning alarms, and they take unsafe shortcuts. Relying on human reliability means those lower controls will inevitably fail exactly when we need them the absolute most. I really want to emphasize this because it's absolutely crucial. It's a core tenet of safety engineering. We have to design the hazard out from the very outset, rather than relying on rules or safety gear to save us later. Good practice demands that we carefully calculate the costs involved to introduce a high-level safety feature and measure that against the actual safety benefit, always striving to keep risks as low as reasonably practicable. You literally cannot just write a rule telling people to be careful and consider the job done. Section 4. Proving it, the safety case. This definition of the safety case is critical.
In the modern engineering world, it's totally not enough to just walk in and say a system is safe or that you followed the pyramid. You have to legally and scientifically prove it. A safety case acts exactly like evidence offered in a court of law to support a claim. You're making the claim, hey, this system is safe. The safety case is the massive mountain of structured evidence, hazard logs, fault tree analyses, rigorous testing data that proves your claim beyond a reasonable doubt to a regulator.
What's super fascinating here is that the safety case concept wasn't actually invented by the railways at all. It originated in the nuclear and offshore oil industries. The stakes in those environments were so unimaginably high that safety regulators basically stopped taking the industry's word for it. They demanded proactive, heavily documented proof of safety before any operations could even begin. And the railway industry, dealing with immense kinetic energy and millions of human passengers every day, very wisely adopted this exact same strict standard. Because these modern systems are so incredibly intricate, it's just no longer viable for an outside assessor to walk in with a clipboard and figure out if it's safe. Only the developer has the deep knowledge required to compile this massive, multi-part document of evidence. We're talking about everything from defining the system boundaries to quality management reports, highly technical safety qualification tests, and analyzing how the system operates under extreme external conditions. It's an exhaustive, living document. Section 5. The Final Defense. Now, to avoid having to reproduce a massive encyclopedia-sized document for every single bolt and wire, every single time a new station is built, the industry wisely breaks safety cases down into 3 distinct types. This is super efficient because it allows engineers to reuse complex safety arguments for standard, proven parts, while still deeply scrutinizing the unique risks of a specific location. Here's how they stack together perfectly in the real world. A manufacturer creates a generic product safety case for the physical hardware, proving the actual computer system won't just spontaneously fail. Then there's a generic application safety case for the standard nationwide signaling rules. Finally, local engineers create a specific application safety case that only looks at the unique geographical layout, the weird curves, and the specific hazards of that one single train station. They all integrate together to form one complete impenetrable safety shield. As we wrap up this explainer, I really want to leave you with a thought to challenge how you view the risks you tolerate every single day. Think about it. Whether it's in your workplace, your daily commute, or even your own home, are you settling for the cheap, unreliable bottom of the pyramid? Understanding exactly how the world's most critical industries systemically manage risk allows all of us to demand better, more robust safety in our everyday lives. Thanks for joining me for this explainer, and definitely keep looking for those hidden systems that keep our world running safely.